Here we go, new hike. So this is Cummins Falls, Tennessee. I don't know if you can clearly see that, but sorry I have not shown any hikes in Arkansas yet. I promise we're going to get there. Some of my favorite hikes are hikes we've done in Arkansas, but we love to go to Nashville. It is like one of our favorite. Anybody been to Nashville before? Tap it in the chat, raise your hand. It's such a great city. It's only like a 6-hour drive, so pretty doable. You don't have to fly there. But you know what makes it nice is when you have places you can stay. One of my best friends lives in Nashville, so we always just go stay with her and her husband. Nashville, there's so many good places to eat. And then you have all this great hiking right around the city within an hour, hour and a half drive. So we did Cummins Falls. This was one of our favorite hikes. To give you a little perspective on how big this waterfall is, you hike down and then you hike along this like creek. It's a pretty decent sized creek. And so make sure you wear like, some athletic sandals or stuff that can get wet, okay, if you're going to go hike this. And then it opens up, here's the end point, and then you turn around and you hike back. Is this kind of swimming, and it is a very popular place to swim when it's warm in the summer. We did it in March, and so it's actually quite cold. But in case you're wondering how big it is, there's my husband. He decided to go for a swim. I just put that in there to give you perspective. This thing is huge. People can get up there and walk on these surfaces, but you have to be very careful because it's moving water. These waterfalls are very big, so it was really spectacular. The water was way too cold to swim, so that's why I decided to just be the one to take pictures. But really beautiful. If you go to Nashville, if you want to do some hiking in Tennessee, Cummins Falls is for sure one you should do. Okay, covalent bonds. So we talked about chapter 3, ionic bonds. And you need to set that totally on the shelf because covalent bonds are a different ball game. We're at a different ballpark. These are different. And we mentioned at the beginning of chapter 3 how covalent bonds are different from ionic bonds. Does anybody remember how they're different? Shared. Yes. What are shared? Covalents are formed by the sharing of electrons. So remember, in ionic bonds, you have two atoms, okay? And one atom is going to totally give an electron to another atom. One atom loses an electron, one atom gains an electron. You have two ions, and the bond is formed between two charged particles, two charged atoms that are now ions. And that does not happen with covalent bonds. All we're doing is we're coming together and we're sharing, okay? So get ions out of your head. We're going to talk about how things are shared. Now, usually, molecular compounds are formed between two nonmetals. If you remember with ionic compounds, we had a metal cation and a nonmetal anion. All right, the metal cation positively charged, the nonmetal anion negatively charged. But here we're mostly dealing with two nonmetals. And in just a second, we'll talk about that on the periodic table. But I want to make a point that we call covalently bonded compounds molecular compounds. Okay, we do not call them ionic compounds. We do not call them crystalline solids. They are known as molecules. So we call them molecular compounds. All right. So there's definitely some differences in verbiage and some vocabulary to get used to for this chapter. Now, if we're talking about nonmetals, what part of the periodic table are we talking about? And what part are we not talking about? So if we were to circle the part that we were talking about, nonmetals are here in the blue and the purple, right? So these are all of our nonmetals and hydrogen. So what we're not talking about, there's a whole large portion of the periodic table we're kind of going to sit on the shelf for a little bit, and that's all these metals. These are not in our covalently bonded compounds, okay? We're just talking about the nonmetals, and so we're zooming in on the blue and the purple elements here. All right. Now, one thing that is the same about ionic and covalently bonded compounds is that all the elements were still abiding by the octet rule. Okay, so do not forget what that says and what that means. The octet rule says that main group elements give or receive electrons to achieve an octet. Well, we're not giving or receiving here, we're just sharing, but we're still trying to get an octet. That's the basis for why and how they share. So the goal of electron sharing is to stabilize atoms by achieving a full octet of valence electrons. We want 8 in that outer shell. And we're going to figure out how we, quote, calculate that or figure that for each type of atom. Now here's a picture of what's actually going on. How do we get a covalent bond if we're sharing? There's two forces at play when atoms approach each other. When they get closer and closer and closer, there's attractive forces and there's repulsive forces. Think about what would be attracting one atom to another, okay? The electrons of one atom are going to feel that positive pull from the nucleus of the other one. And then vice versa. The electron cloud from this atom on the right is going to feel the positive pull from the nucleus on the left. There's also repulsive forces though, okay? Because a positive and a positive nucleus, okay, we feel the repulsion between those as well as the two electron clouds, the negative electrons from each atom. They repulse one another. Now, why do we get a bond? Okay, it's because the attractive forces are stronger than the repulsive. And that's probably, you know, well, duh, but that's what's happening. Those attractive forces are stronger. They overpower the repulsive forces, and we end up getting those atoms to stay close together, and you get a bond, okay, with sharing electrons. All right. Any statement in red today, by the way, there'll be like 2, I think, and this is the first one. This is kind of a motto or a mantra that will really help you if you honestly memorize it, all right? Anytime electrons are shared, both atoms in the bond claim all the shared electrons, okay? Anytime electrons are shared, both atoms in the bond claim all the shared electrons. So what do we mean by that? How does that look? Well, if we're trying to get an octet, by sharing one, you kind of gain one. And so look how that plays out with the molecule of hydrogen. We have 2 hydrogen atoms, and they approach one another, and they form a covalent bond. Each one starts out, if you remember, hydrogen just has 1 proton, 1 electron. So you see that 1 electron in each hydrogen atom. And as they approach one another, okay, now they're going to share. And here's the shared electron pair. You can draw it as just 2 dots here representing the 2 electrons. There's also other ways to represent this. We get some overlap in the spheres that we initially had. Each one is a sphere on the left over here. And then we have this oval shape. So the shape of the molecule changes a little bit. But the way we can represent the bond, kind of the shorthand notation, is a dash, a line, or you could write the molecule like this, H2. Or you can keep it as that electron dot pair. We are mostly going to be using lines to represent covalent bonds, okay? That's what we're mostly going to use. I don't know why I put 2 spaces here, but a line or a dash, if that's what you want to call it, line or slash dash, that's how we can represent bonds. Here's another example with chlorine. Oh, by the way, is hydrogen satisfied now? Did we achieve the octet we were talking about? Well, remember, hydrogen and helium are 2 exceptions to the octet rule, okay? Hydrogen and helium are exceptions to the octet rule. Okay, hydrogen and helium are satisfied when they have 2 electrons in their outer shell. Because something crazy about that very first energy shell around the nucleus can only hold 2 electrons. So once they hit 2 there, they're full and they're done. So hydrogen is satisfied here. It's just that it's not because of it, it's an octet. But chlorine does abide by the octet rule. So if you notice, chlorine, if we draw the electron dot structure, so don't forget how to do those, you just draw the number of dots that corresponds to the number of valence electrons for that element. So chlorine is in main group what? Anybody remember? It's a halogen, and halogens are main group 7. Thank you, Janelle. So we've got main group 7, so we've got 7 electrons drawn around each of these chlorine atoms. If you'll notice, all of them are paired up except for 1. All right, we have space for 1 more electron to come in right here on this unpaired side. So if 2 chlorine atoms approach, they both want to pair up that final electron. So if they share, then they can do that. And by doing that, each chlorine atom claims all these electrons. I'm going to circle this one in a different color. This chlorine atom on the right claims all these electrons. So if you now count all the electrons in those respective boxes, each chlorine claims to have 8 electrons, okay? They both claim all the shared electrons. So now they both have an octet and they're both stabilized and satisfied, okay? This picture down here on the bottom is just to kind of show you how those electrons are coming together. You really don't have to worry about the shapes of those because, again, we're not getting into electron configurations. All right, diatomics. Questions so far on what it looks like to share those electrons and understanding that concept of both of the atoms in the bond claim those electrons. Any questions? Okay. Diatomics. What is a diatomic? So there's certain elements that naturally exist as two bonded atoms. They naturally exist as a molecule. They do not exist as single atoms. So because of that, we will not write diatomics as a single atom. All right. So what does that mean? Well, here are the 7 elements that naturally exist as diatomics. And you need to memorize these. There's just no way around it, but it's not hard. One key thing is here, they actually form a figure 7 on the periodic table. All of them except hydrogen. So hydrogen is one, and then nitrogen, oxygen, and your halogens. Okay, and here's the 7 I was talking about, right? So there's 7 of them. They look like a 7 on the periodic table. When you write fluorine or chlorine or hydrogen or whatever, you have to write it as a molecule. That is how it naturally exists. After we get done with chapter 4, we're going to move into chapter 5, which is all about writing chemical reactions. And if you have hydrogen and chlorine reacting together to make hydrochloric acid, okay, and you told me this, I would count you wrong. Okay, why would I count you wrong? Because in nature, hydrogen and chlorine, they exist as molecules. You have to know, you have to write them correctly as a reactant when they're by themselves. So the correct way to do that, we'd have to balance it, of course. We'll get into that later, but you cannot write them in this bottom picture as that's incorrect. We don't want to write them as single atoms. Okay, so anything that's a diatomic, you have to write as a molecule, 2 bonded atoms. All right. So we're also going to start understanding how these atoms are spaced together. We're going to spend a little bit more time on, we're going to start with electron dot structures and how the atoms come together and share the electrons, and then how they claim all the shared electrons and how that satisfies the octet rule. So let's look at these 3 molecules right here. Water, ammonia, and methane. Okay, these are 3 very common molecules that we'll be talking about in the course from this point forward. So let's look at water. We're going to draw the electron dot structure, and we're going to see how they form their covalent bonds. So you see the bonds right here, but how does all this start out, and is everybody satisfied with the octet rule? So first, let's draw oxygen. You guys remember, oxygen is in main group what? Six. So give it the appropriate number of dots or electrons. We want to give it 6. 1, 2, 3, 4. 1 on each side. Now I can pair up 5, and I'm going to pair another one on the bottom. So oxygen wants to have how many? 8. Okay, so it needs 2 more. Remember, every time it shares one, it's going to get another one. It's going to claim both. So if we have a hydrogen that comes along for the water molecule, hydrogen is main group 1, so it has 1 valence right here. Okay, so if these agree to share, now what they're doing is they're saying, okay, here's a bond. And guess what? Oxygen claims both of those electrons in that box I just drew. The one it owned originally and the one that hydrogen is sharing. Well, guess what? Hydrogen also claims them. That's just the agreement when you share. They both claim them. So now how many electrons does oxygen have? We had 6, shared
7.
1, gained 1. Now we have 7. We're almost there. So if it shares again, we know a water molecule has 2 hydrogens, okay? So now they're going to share these electrons. Now oxygen claims all those shared electrons. So it has 4 that it totally owns that it's not sharing. And then it's got 4 that it, via sharing, also claims. So now it has a full octet, okay? So you see how that happens? Hydrogen is also satisfied. So let's do that with ammonia. Draw the dot structure for nitrogen. Nitrogen is what we call the central atom here. It's in main group 5. So we'll give it 1, 2, 3, 4, and we'll pair up that final one, electron. So there's its 5 valence electrons. It needs 3 more to get an octet, right? We're 3 away. So if we have a hydrogen come along, because ammonia has 3 hydrogens, there's its electron. They're going to share both of these. So these are going to form a bond. Nitrogen claims both now. So does hydrogen. Now nitrogen claims and has 6 valence electrons. So we're getting there, but we still have work to do. So there's another bond it's going to form. It's going to share again. Now it claims both of those as well. Now it has 7. We have 1 unpaired electron left. So if it does it again, now we get 8. Okay, so you see how the octet is satisfied by sharing each time. You'll notice, and different atoms will look different, but oxygen was left with 2 lone pairs. Okay, there's one and there's the other one. Nitrogen had 3 bonds, but it was still left with 1 lone pair. Okay, so not all the atoms will look the same. Some will have different numbers of bonds and different lone pairs when their octet is satisfied. Let's look at carbon. Carbon has no lone pairs on it. So carbon starts out, it's main group 4. So here is the 4 valence electrons that it starts out having. It's 4 away from an octet, so it needs 4 more. Can we do another example slower? Yes. Janelle, I'll go through this slower. So we have 4 valence electrons because carbon is main group 4. So we've drawn those as 4 dots around the carbon. All right, so how many more does carbon need to get an octet? We need 4 more, okay? So it can share with any element. Our example here just happens to be hydrogen in every case. So hydrogen has 1 electron to share. Okay, so when it shares with carbon and carbon shares one of its electrons with hydrogen, both carbon and hydrogen claim both of these electrons in the box. So now carbon claims 5 electrons. So it's technically, by sharing, it's gained 1. You see that? Every time you share 1, you gain 1. So let's do another one with another hydrogen. Hydrogen comes along, it has 1 electron to share. If it shares again, now carbon claims both of those as well. The one it originally owned and the one that hydrogen is sharing. So now carbon has 6. So we're close to an octet. If we share again, now how many does carbon claim? 2, 4, 6, and then that one up top, 7. So we need to share 1 more time for carbon to get 8. So carbon has to share all 4 of its electrons to get an octet. Nitrogen only had to share 3 because it started out with 5, and oxygen only had to share 2. Okay, I have a question in the chat. Since nitrogen is a diatomic, why don't you have to draw 2 nitrogen atoms? Well, that's when nitrogen is by itself. Okay, diatomics are only when the element is by itself and not bonded to any other thing. Here, nitrogen is bonded to hydrogen. Okay, so diatomics are only for when you're writing the element by itself as a pure substance. Does that make sense? Yes, Janelle, if everyone will read that in the chat, the goal is to share until you get 8. That is the goal. We want to satisfy the octet rule, and you do so by sharing electrons. That's the whole premise of the covalent bond. Okay? So those are just some examples. We're going to do many more examples today. Here's the other quote that I want you to kind of, I think will help you. Every time you share an electron, you gain an electron. That should help you as you're drawing these out to remember that. So here's some questions to ask yourself if you're trying to figure out, okay, I have this molecule and I need to know how many bonds it's going to form, or I have this atom, I need to know how many bonds it's going to form. Well, here's the questions you ask yourself. First off, how many valence does this element have starting out? Notice for oxygen, nitrogen, and carbon up there, we said, okay, starting out it has this many valence. Starting out it has 5 valence or 4 valence, and we draw those. Okay, so first figure out how many valence electrons does that element have. Draw them in. Then, second question, how many electrons does this element need to get an octet? So for example, oxygen started out with 6. It owns 6 because it's in main group 6. So it only needs 2 more. The number that the element needs varies depending on how many it already has. Okay, once you figure out how many it needs, this last statement helps answer that question, how many bonds is it going to form? The number of electrons an atom needs to achieve an octet is equal to the number of bonds it will form. If you notice that. Oxygen needed 2 more electrons. It had 6. 6 plus 2 is 8, so it formed 2 bonds. Nitrogen needed 3 more. Okay? And so it forms 3 bonds. Carbon started out with 4, and because it needs 4 more, it shares all 4, and then it gets the octet. Hold on, let me respond to a comment. All right, any questions there? All right. So this picture right down here is a figure from your textbook, and it actually shows you how many bonds each of the nonmetals typically forms. And I say typically or usually because there's some exceptions, and we'll point out those exceptions in a minute. All right, so if we're looking at this figure, it shows you that up top, this information is the number of valence electrons for that particular element or group. And then underneath, it shows you in red text the number of covalent bonds that that particular element will form. Okay. So most everything is pretty predictable or pretty straightforward, but there's a couple of these elements that have exceptions. And if you'll notice, for example, I'll point one out right here, phosphorus. Usually it forms 3 bonds, just like nitrogen, because they're in the same group. But occasionally phosphorus will share all 5 of its valence electrons. All right, and let's look at how that happens and what that does. If phosphorus, I'm going to draw the electron dot structure. I'm going to put the 4 valence around it, actually, sorry, 5. And if it shares all 5, so let's say 5 hydrogens come along, and they all share one as well, an electron that is. Now phosphorus claims how many electrons? 10. Thank you, Brendan. Phosphorus claims all 10 of those. It originally owned 5, and remember, every time you share one, you gain one. So this exceeds the octet rule. Okay, it has 10. Look at sulfur. Sulfur, here's an exception. Sulfur can share all 6 of its valence electrons. And when it does that, it will have 12 valence electrons. That is way beyond 8, right? So there are some exceptions. I'm not gonna really have exceptions on the exam. I just want you to know what those parentheses are there for. I'm not gonna go find the most obscure exception and then drill you on that. So I want you to know that those are there, but I want you to focus on the number that they typically will form, the number of bonds, that is. All right, we have our first poll question that's going to come up. If you notice, at the bottom of the slide, there are 4 molecules. I want to know if these are, what I'm going to say, legal. Can these be real molecules, or do these violate our rules? Okay, so let me pull the poll up. All right, so first one is A, correct possible molecule, B, C, and D. So look at the number of bonds that each atom forms and see if it matches what it should, and figure out, is that a legitimate molecule or is that incorrect? We'll talk about these afterwards. All right, you should be getting your answers in. About 12 more people. Go ahead, get them in. We are pretty evenly divided on almost all of these. So I'm glad we're doing this. All right, 5, 4, 3, 2, 1. All right. So here were the answers. A, 25 said yes, 21 said no. Okay, let's look at this. Carbon, let's just look at carbon. It's the middle atom. How many bonds does carbon have? How many can you count? I see different numbers, people holding up different numbers. Carbon here in this molecule, I'm only seeing 3 bonds. 1, 2, 3. How many should carbon have? Look up here, it should have 4 bonds. So if each line here connecting a carbon to a bromine represents how many electrons? Each dash, each line that connects atoms represents 2 electrons, remember? So how many electrons does carbon claim? It only claims 6. There's 2 electrons here, 2 electrons in that one, and then 2 electrons in this one. That's only 6. We're too short of an octet. So this is totally not acceptable. Carbon is one of the elements that never, ever, ever has exceptions. It will always form 4 bonds. Never 2, never 3, never 5, 4, always 4. And it will never have a lone pair, okay? Never, ever put a lone pair on carbon. So that is not an okay molecule. So the minority got it here. This will not happen. How could you fix this to where it could be okay? How could we edit this? If we put another bond to bromine, I'm going to draw over that molecule right here, then that would be acceptable. But, okay, yes, thank you, put another bromine. All right, let's look at the next one. You have an atom of iodine and chlorine. 27 people said yes, this is possible. 19 said no. All right, well, let's look over at iodine and chlorine. Here we go. Iodine, 1 bond, and chlorine, 1 bond. So what you don't see on this molecule are the electrons that they own, okay, the electrons that they're not sharing. So how many valence does iodine and chlorine have if we draw that out? Should be 7 because they're halogens. So there's iodine and there's chlorine. They both have 7. So they only need 1 more to get an octet, right? So if they both share 1, they both share that unpaired electron, then you have this bond right here. Now they're satisfied, all right? I know that it's not showing the lone pairs, it's only showing you the shared electrons, but we don't see electrons, all right? So that's why they haven't drawn all these lone pairs in, but this is a totally viable molecule. 1 bond, everybody's satisfied, so yes, this could happen. Okay, now let's look at C. So we have fluorine and 4 hydrogens. 17 people said yes, this is possible. 29 people said no. Okay, so fluorine is also right here. It should only have one bond. We have a molecule where fluorine has 4. Fluorine starts out, again, it's not showing you all the valence, but this is how fluorine looks. Just like the iodine and chlorine we just drew, this is how many valence it has, starting out before it shares anything. So how many does fluorine want to share? Just one, all right? So one hydrogen comes along, they both share, everybody's satisfied. Done. We cannot have that. That is an exception to the octet rule. Fluorine would be, if we had this, that's acceptable, okay? We can't have 4 bonds on fluorine. So, no. C is not possible. All right, D, 37 people, 80% said yes, 20% said no, okay? So sulfur is in main group 6 right here under oxygen, so it has 6 valence electrons. 1, 2, 3, 4, 5, and I'll pair up another one out here. So just like oxygen, when we drew the water molecule earlier, it only needs 2 more to get the octet. So it's going to share once, and then it's going to share again, and now it has an octet. In the chat, Angelina, correct. Yeah, if you did that, it's if we had C as a molecule, fluorine would be over the octet rule, and fluorine is not an exception. It has nothing in parentheses underneath. It only shares 1 bond. Back to molecule D. Yes, this is totally possible. This totally meets the octet rule here for everybody. Hydrogen is satisfied. Both of these hydrogens claim 2 in the shared bonds, and then sulfur has a full set of 8 once it's done sharing the 2 unpaired it started out with. So it was no, yes, no, yes. So I'm glad we did that because I think there was maybe some confusion. We're going to do more examples again, so if you're not totally comfortable with this stuff, I don't expect you to be yet. We have a lot more work to do. So let's talk about for a second, though, what happens when you have what we call a multiple bond. So this can happen different ways, but here's an example with oxygen. If we have 2 oxygen atoms that are going to bind together because we know they exist as a diatomic, they each have 6 valence electrons, right? They're in main group 6. So what you see left and right here are the 6 electrons that they start out with. So if they both initially share 1 electron, let's draw a picture of what that looks like. Let's say they share the ones in the middle here. And then they still have all these other electrons that they started out with. And these are in the box are the ones that are shared. Now how many does each oxygen claim to have? 7, Brendan, yes. So each oxygen has 7, but this is not stable. Okay, it wants 8. So what can they do? They don't have any other atoms to share with. It's just the 2 of them. So they both agree, let's share again. So they're going to share those original 2, and now they're going to share 2 more. All right, they still own the 2 up top and the 2 on the bottom, but they're going to share both of their unpaired. So they have a bond here and a bond here. And they claim, remember, the first thing we said is both atoms in a bond claim all the shared electrons. So now how many does each oxygen have? It owns 4, and it claims all the shared electrons, which is 4 more. So now each oxygen has 8, and this is stable. So for oxygen to bond with itself and be stable, they have to share twice, and we call this a double bond. All right, let's look at another example of a double bond. Let's talk about nitrogen. Starting out, we know nitrogen has 5 valence electrons. So you see that on each nitrogen atom, that's going to be a part of this molecule. So if they both share 1, let's say they both share the ones I'm going to circle. So nitrogen on the left now looks like this. And it's going to share the one on the right. And so now they both look like this. Now how many does each nitrogen have? They started out with 5. Now they both have 6. So this is not stable. So they're like, all right, if you up 1, I'll up 1. Let's both share again. So there's the 2 they originally shared. They're going to share again. Notice they have 3 unpaired electrons that they can share. So now each nitrogen looks like this. They have shared the unpaired electron on the left, and they've both shared the unpaired electron on the right. Now each nitrogen has 1, 2, 3 unpaired or unshared and 4 that are shared. So they both claim 7. But this is still not stable. So they have to share again. So now they're going to share all 3 of their unpaired electrons. Here they were sharing 2. All right, or I said they were sharing them. It didn't matter which 2, but all right. So now here's what this looks like. They are sharing in between them 6 electrons, and then they still have 2 that they're not sharing. And they both claim all of the shared electrons. So that's 6 plus they own 2. So 6 shared plus 2 owned, and that equals 8. So this is stable. So you see nitrogen, when it bonds with another atom of itself, which is how it exists in nature, it's only stable when it has what we call a triple bond. So you can have single bonds, double bonds, and triple bonds. And there's a place and a purpose for each of those. Questions on single bonds and double bonds? I have another poll because I want to get your thoughts. So look at this poll. You need to remember that we said elements within the same group behave similarly. That's a concept from chapter 2. When we studied the periodic table and how it was organized and divided, we said elements in the same group, the same vertical column, they behave similarly. So based on what we just talked about, how many bonds do you think each of these elements would form in the poll? Give you maybe 30 more seconds. Still got like 20 people need to vote. So phosphorus is in the same group as nitrogen. Sulfur, if you notice, is in the same group as oxygen. And fluorine, well, we've actually already talked about fluorine. But okay, we're almost there. I'm going to go ahead and call it 5, 4, 3, 2, 1. All right, so phosphorus, everybody said, well, most people, 75% said 3 bonds, so a triple bond. phosphorus is in the same group as nitrogen, so it starts out with the same number of valence. So if you had what does a molecule of phosphorus mean? That is P2, 2 phosphorus atoms. So it's going to do exactly what nitrogen would do. You could literally just substitute the N for a P, and you'd see the same thing, okay? So you're going to get a triple bond there. So 3 was the correct answer for number 1. How many bonds would a molecule of sulfur? So sulfur is in the same group as oxygen. So we're talking about this. A molecule of sulfur is 2 sulfur atoms coming together. They both start out with 6 valence electrons. They both want to gain 2 more, so they both have to share 2. If they're both sharing 2, that's a total of 4 shared electrons. That's a double bond. And that's exactly what we saw down here with oxygen, okay, is the double bond. Okay, fluorine. Fluorine has 7. So fluorine, we're talking about F2. And each fluorine atom has 7 valence electrons. So both of them are just going to share 1. All right. So you'll get something that looks like this. They're sharing 1 because they still own, and they don't share those other 6. So a single bond is what's going to happen with a molecule like that. Okay. Good deal. Well, let's move on. We're going to get into Lewis structures. We're going to spend the rest of lecture today on Lewis structures, and hopefully we'll get to condensed structures. What is a Lewis structure? They are a way to visualize the way the atoms are connected or bonded, okay? It's how you visualize, which one's in the middle, which one's on the outside. And essentially what you've noticed is we've kind of started out with the electron dot structures. Lewis structures are just an extension of that, where we draw the shared electrons as a line, as a bond, okay? So if we have the molecular formula SH2, we can know what atoms and how many of each atom are in the molecule, but we have no idea how it's arranged. Is the hydrogen in the middle? Is the sulfur in the middle? We don't know, but the Lewis structure tells us, okay? The Lewis structure would tell us, well, here's how they're arranged in the correct order. We have the sulfur in the middle, hydrogen's on the outside, sulfur has 2 lone pairs. Things like that we cannot see or understand just from a molecular formula. And so that's what Lewis structures are helpful for. We have water here. We've seen that oxygen has 6 valence electrons and each hydrogen has 1. So if hydrogen shares both the unpaired, oxygen wants 2 more. And then we see what it ends up looking like is this. And we know oxygen's in the middle and the hydrogens again are on the outside. Hydrogens, just so you know, they'll always be on the outside. And then what we've talked about too, and what we've seen is that there's certain atoms that are going to end up with lone pairs because they didn't need to share those electrons. They were satisfied with an octet only by sharing a couple of electrons, not all of their electrons. But then some atoms, like carbon right here, doesn't have any lone pairs. And I'm going to make a big deal out of this. Carbon will never, ever, ever, ever have lone pairs. Okay, I say that, and I guarantee you somebody on exam 2 will draw a carbon with a lone pair on it. It inevitably happens every semester. Please do not let that be you. Okay, I will count off mega points if you put a lone pair on a carbon. All right. But it's okay if you put lone pairs on oxygen and nitrogen and sulfur and other elements because they're satisfied with an octet before they have to share all their electrons. So this next slide, we're going to draw what some particular elements should look like in a covalently bonded molecule. Just to give you some guides and some tracks to run on, what could a carbon look like? Well, carbon, if it doesn't have any lone pairs, that's because it shared all 4 of its valence to get the octet. So it should always have 4 bonds, but that can happen different ways. Carbon could look like this, okay, where it has 4 single bonds, okay? But it could also look like this, where it has 2 single bonds and a double bond. Guess what? Carbon could also look like this. That's 4 bonds. No single bonds. Carbon could also look like this. A triple bond and a single bond. We sound like we're ordering at McDonald's, right? Give me a single and a double. Give me a triple and 2 doubles. Just kidding. So these are all 4 bonds, but they can be arranged different ways. Nitrogen. Let's talk about how nitrogen can look. Nitrogen has to have 3 bonds, but they can be arranged different ways. We've already seen that nitrogen can have 3 single bonds. And guess what? It should always have a lone pair. So 3 single bonds and a lone pair. It could have a double bond and a single bond and a lone pair. Nitrogen can also, when it's bonded to itself, we saw this, it can have a triple bond. And then it would still have a lone pair. What is the difference between pairs and bonds? Okay, a lone pair is a pair of electrons that the atom is not sharing. It completely owns those, does not share. A bond is shared electrons between 2 atoms. So bonds are made up of shared electrons, but lone pairs is a pair, 2 electrons that are not shared. Okay, does that make sense? Janelle, did that answer your question? Okay. Oxygen. What will oxygen look like? Well, oxygen starts out with 6 valence. Remember, it's going to share 2 because it wants to gain 2 to get the octet. So if it shares 2, it could look like this. And it will have 2 lone pairs. So 2 single. And then 2, I'm going to abbreviate lone pairs. It'll always have 2 lone pairs though. And then it could also have a double bond, right? So that's how oxygen could look. Halogen, we're talking about fluorine, we're talking about chlorine, bromine, and iodine. These guys have 7 valence electrons, right? So they only want to share 1 electron. When they do, they have an octet, they're stable, they're done. So they're only going to have 1 bond. So I'm going to put an X here to represent any one of those 4 elements. Here's the element or electrons that they own, and then they're going to share that other electron in a bond. They'll never look any different. So 1 single bond. And then 3 lone pairs. They will always look this way. Hydrogen, it only has 1 electron to share. No lone pairs, just 1 single bond. That's all it will ever do. Okay. So what we just did is we created kind of a key for you. I would keep this slide handy. As you are drawing Lewis structures, you need to go back and check, okay, does my carbon look like one of these 4 carbons we drew? Does my nitrogen look like one of these 3 nitrogens we just drew? Now, here's the deal. It does not matter if I drew this or these are synonymous. Okay, these are the same. It doesn't matter where you put the lone pair around the nitrogen. Okay, what matters here is that it has a triple bond and a lone pair. Okay, so these are all the same. So what I'm just saying though is when you get done drawing a Lewis structure, you want to check yourself. Say, does it match something that I just drew on this slide? Okay. Here's some examples just with 2 different molecules. If we look at these carbons right here, what do you notice? Is that legal? What's drawn? Each carbon has 4 single bonds. Each hydrogen has 1 single bond. This is very common. The carbons are usually piled in the middle because they can form 4 bonds. They're very good central atoms. because they can connect to a lot of other atoms. Hydrogen, 1 bond, so they're always on the perimeter. They're always the exterior atoms, okay? Look over here. Both of these carbons have 4 bonds. Check, check, but they look different, right? It's just because one's a double bond and 2 single bonds for the carbon on the right, but 4 single bonds for the carbon on the left, but that's 4 bonds in both cases, all right? So just to give you some visuals, they can look different, but just make sure they always have the correct number of bonds. All right, we're going to go over the 5 rules for how to draw Lewis structures. Don't worry about memorizing these word for word, but you need to be able to follow the steps for sure. It'll guide you on how to draw them, because let me tell you, I'm going to turn you loose in just a second, and you're going to be like, I don't know how to draw these. Well, remember these rules, go through them step by step. They'll guide you every single time. So first, you're going to find the total number of valence electrons of all the atoms in the molecule or the ion. So I'll show you how to do that. Then, once you've done that, you will draw a line between each pair of connected atoms to represent the 2 electrons in the covalent bond. Once you've connected your atoms, you're going to use the remaining electrons, and then you will add lone pairs. Okay, so that each atom on the perimeter, each atom that's connected to a central atom, except hydrogen, because hydrogen does not get lone pairs, but you want every atom to get an octet. Okay, except hydrogen, he does not get any lone pairs. All right, and then place any remaining electrons, I should say as lone pairs on the central atom. Last rule, if the central atom still does not have an octet, after you've put all the electrons on that could possibly be there, take a lone pair from a neighboring atom and form a multiple bond to the central atom. We're going to do some practice problems, but a really good example of this, let's look at the molecule carbon dioxide. I actually forgot to do this morning. I'm just going to, down here in this blank space, let's look at CO2. I want you to figure out, we have 1 carbon and 2 oxygens. How many total valence electrons do we have in this molecule? So carbon, we have 1 of them. Each carbon has 4 valence. So that's 4 contributed from carbon. Oxygen, we have 2 oxygens. Each one has 6 valence. So that's 12. So total we should have 16 valence electrons in this molecule. So when I say add up the total, kind of do something similar to that, all right? Now, let's follow our next rule. If you're looking at the slide previous, it said start connecting atoms. You're going to draw a line. So which atom, how do you think these are going to be arranged? Do you want to put an oxygen in the middle? Do you want to put the carbon in the middle? Carbon. Really, carbon's always your best bet, okay, as the middle atom. It can form the most number of bonds. So I'm just going to connect carbon to an oxygen, carbon to an oxygen. So I've used up all my atoms, but I still have a lot of electrons to represent, right? How many electrons have I drawn so far in my structure? 4. Remember, each line represents 2 electrons. So we've represented 4. Now rule number 3 said start putting lone pairs on the atoms that are connected to the central. So this is your oxygen. So I'm going to put lone pairs until every oxygen gets an octet. Okay. Every oxygen has an octet. How many electrons do I have in my structure now?
16.
16. So we've used up all of our electrons, but what's the problem?
The carbon doesn't have 4 bonds.
Carbon does not have 4 bonds. We violated that carbon. Okay, so rule number 4 says when this happened. Actually, I think this is rule number 5. Let's go back and see. Yeah, we didn't have to do rule number 4. Okay, we filled up, we used up all the quota of electrons we had, so we did not have any remaining electrons. So we didn't have to do this. Put lone pairs on the central. And by the way, you'll never put lone pairs on carbon, remember? But let's check out rule number 5. If the central atom does not yet have an octet, and it does not, then we take lone pair from a neighboring atom and we make a multiple bond. So what that is telling us to do, I'm going to erase a lone pair from oxygen. I'm going to put a double bond to carbon. Is carbon satisfied yet? Does it have an octet?
No.
Not yet, so I'm going to do it with the other oxygen as well. What about now? Do we still have 16 electrons in our structure? Yes. Does carbon have 4 bonds? Yes. Does each oxygen have 2 bonds, 2 lone pairs? Yes. So boom, we're done. Okay. So that was just an example step by step of how to walk through those rules. Okay. We're going to do 1 and 2, and then probably the others 3, and then look, I have 3 more on the next slide as well. I'll probably let you practice those on your own or attempt them on your own. But let's walk through the first 2 together, and then we'll see how we're doing with time. So rule number 1, add up the total valence. So do this for number 1 and 2. While y'all are working on that, I've got to grab a drink of water. All right, so how many electrons did y'all get for number 1?
The 21.
28? Did y'all get 28?
I got 21.
21?
Is it supposed to be 28?
Anybody get something different? Brendan said 26. So 21, 26, or 28? Courtney, Ashlyn, Meredith confirmed 26. It should be 26. Let's see. Carbon, we have 3 of them. Each one has 4, so that's 12. Hydrogen, we have 8 of them. Each one has 1 valence, so that's 8 there. And oxygen, we have 1 oxygen. Each one has 6 valence, so that's 6 there. 12 and 8 is 20, should be 26. All right. So here's what I like to do. We have 12 atoms, right, to draw here. 12, 3 carbons, 8 hydrogens, and oxygen. How are we going to piece these together? Well, I'll tell you this. There's probably more than one valid way to do that. We're just going to pick one and go with it. If you get a structure that's different than mine, but it meets all the requirements and the number of bonds and everything, it might be another different valid structure. I like to go ahead and just connect all my carbons. Like that. Okay, and then, as we saw earlier, hydrogens are usually on the perimeter. So I'm just going to start putting hydrogens on these carbons until I run out of hydrogens, okay? Okay, so that first carbon now has 4 bonds. I can't put any more atoms on it, so I'm going to move over to the next carbon. Okay, now that second carbon also has 4 bonds. So far, I've drawn in 5 hydrogens. I've still got to do 3 more. Okay, so I've drawn in all the hydrogens and all the carbons. So I still have to draw my oxygen. I haven't put that yet. Is there a spot that I could put that? No. So what I've drawn, we can't have that. I don't have any spot for my oxygen. How do I know this? Well, all the carbons have 4 bonds. All the hydrogens have a single bond. There's no spot for the oxygen. So we've got to erase I'm just going to erase one of these hydrogens. I'll erase that last one. So instead of putting a hydrogen there, what if I put my oxygen there? Okay, I've still got to draw that last hydrogen in, and where can I put it? Oxygen is supposed to have 2 bonds, 2 lone pairs, right? And I cannot double bond it to that carbon. Why not? That's a violation too. Now carbon has 5 bonds. Carbon will never deviate. It always will have 4 bonds. Never 5, never 3. So I cannot double bond it. So what if I put that hydrogen on that oxygen? And then oxygen should have 2 lone pairs, right? So once you get everything drawn in a way that makes sense and it fits the puzzle pieces that we kind of drew earlier, you need to do the last thing, double check, have I drawn in 26 valence electrons? So I just will sometimes number them off. Remember, every line represents 2 electrons. So there's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and then a lone pair is 2 more. That's 22, 24, and then 26. So yeah, we're good. You could have drawn it a different way. Guess what? Sometimes you'll see an oxygen bonded between a carbon and a carbon. And then you put all the hydrogens around the carbons, okay? This would be a valid structure too. All right, number 2, and then we're going to move on. I want you to do the total number of valence. Okay, so we have 2 carbons. There's 2 of them, and each one has 4. We've got 5 hydrogens. Each one has 1 valence electron. So that's 5 total from the hydrogens. Fluorine, we've got 1 fluorine. Each fluorine has 7 valence, so that's 7 from fluorine. 1 oxygen. 26 again. So now, kind of like we did last time, go ahead and start pairing things up. Here's what you know. Hydrogen and fluorine will never be central atoms because they can only have 1 bond. So anything that you're going to put as central or you're going to connect other atoms to needs to be a carbon, or in this case, an oxygen, since you have oxygen structure. So you could either do this, or you could do these are the 2 options you have. Because this is just, these are synonymous, right? It's just a 180-degree flip. So these are the same. So your 2 options are either the top chain or the bottom. So let's look at the top one. We've got 5 hydrogens. So again, I'm just going to start putting hydrogens on carbons. Whoops. So there's 5 hydrogens on the carbons. Now what do we have left? We have not drawn in our fluorine. This oxygen only has 1 bond so far. We have to have a second bond on oxygen, and we cannot double bond it. I cannot draw a double bond to that carbon. Okay, because that would give that carbon 5 bonds. We cannot have 5 bonds on a carbon. So what if we bond that oxygen to fluorine? Okay, fluorine can only have one bond. How many lone pairs is it supposed to have? It's a halogen, so it needs how many lone pairs? Not just one lone pair, it needs more than one lone pair. 3. 7 valence, Angelina, or who said Connor? Sorry, but 3 lone pairs, Angelina. Yeah, just like that. And then I think we're missing some lone pairs on our oxygen. How many go on the oxygen? Yeah. And then we need to double check. How many electrons have we shown in our structure total? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and then 22, 24, 26. So we're good. And again, you could take this bottom structure and fill in the other atoms as well. And I bet you could get a valid structure that way. Well, guys, we are nearly out of time. And we do not have enough time to get into condensed structures, so we have more than I hoped we would have to go over on Tuesday, but we will pick up with condensed structures on Tuesday and move on from there. So any questions? Oh, I have one last poll. We have 2 minutes. Let me do this last poll. And someone had a brilliant idea. I won't name names, but they're in this lecture, to do a poll about how much students comprehended at the end of lecture. So guess what we're about to do? I want to know, how much do you think? There's 3 questions on this poll. First off, question number 1, kind of a review here. The number of valence electrons an element already has is equal to the number of bonds it will form. Is that true or false? The number of valence electrons that an element already has equals the number of bonds. Question number 2, how many bonds will silicon form in a covalently bonded molecule? You need to go see what group is it in. You need to ask yourself, how many valence does it have?